Alright guys, welcome back. Part 3 of visual displays of data, bars and boxes, right? So some bar graphs, a round pie chart, some advice on graphing, and a set of box and whisker plots. Some of my favorite because they remind me of cats. Okay, bar graphs. Bar graphs are a lot like histograms, right? They have bars that represent something on the y-axis. Now in the histogram, remember, it was always frequency on the y-axis, because in a histogram we are simply talking about the relative frequency of various values on the x-axis. Because of that, the x-axis is a continuous variable in the case of a histogram, right? An interval continuous variable. The bar is always touched in a histogram. In the case where you have a nominal, categorical, or even ordinal independent variable, something like month of the year, right? They're in an order. They're not all the same length. Some are 28, some are 30, some are 31 days. But there is an order. If you were to, say, represent the number of students born by any particular month, right? I was born in January, maybe you're December or February or wherever else. We count that number and we can represent that on the y-axis. In the case of a bar graph, because the IV is nominal or ordinal, the bars don't touch. That's to represent that these are distinctly different spots on the scale, and that there are not spots in between as there are with a continuous interval variable. So a histogram, it's always frequency on the y-axis, and it's always an interval continuous variable on the x-axis, and the bars touch. Bar graph, it can be anything on the y-axis, whatever that dependent variable happens to be, usually something interval in nature. And then it's usually a categorical nominal variable on the x-axis, and the bars do not touch. Now, the graph on the right's not the best because I feel like there needs to be more space between those bars, but it's a good example of what they call the Pareto chart. Pareto chart is simply taking the points of the scale that are on that x-axis and reordering them so that the bars go from smallest to largest or largest to smallest to sort of more clearly represent the difference in the height of the bars. So in this case, the reason why you're late to the airport or to school or to whatever, the lowest frequency of that was emergencies. The highest frequency of causes for late arrivals is traffic. And putting it in that Pareto chart allows you to very quickly see the relative sizes of those. Now, just like we could before, we can still lie or mislead with bar graphs. So take this example. Maybe I'm presenting these data again to Congress or to some other politician. I want to lobby for change. And I say, okay, I'm trying to show you the fairly dramatic difference between how strongly people intend to stay in the Navy if they've not been sexually harassed versus when those same female naval officers have been sexually harassed. I'm trying to show that once you've been sexually harassed as a female naval officer, you have far lower intentions to stay in the Navy. So I present to you these data where you can see the green bar higher than the blue bar. But realistically, a critic could say that green bar doesn't look to be very much higher than that blue bar. Right, on a scale of 0 to 4, right there in intentions to stay, they look to be pretty close. And so it actually could make the argument that while sexual harassment certainly declines or lessens their intentions to stay, it doesn't have a dramatic effect. But what if, instead of representing the entire y-axis over there from 0 to 4, the entire length of the scale, I instead did a range frame. And I said, well, nobody actually ever gave an intention score lower than 3.3. Out of everybody I completely asked, everyone rated somewhere between 3.3 and 3.7, right? Or 3.8, let's say. So I'm only going to show you that portion of the scale. So a range frame. Here's our range frame. Now we see it goes from 3.3 to 3.7. Now look at what I'm able to represent. What looks to be a huge difference in intention to remain in the Navy. And so be aware of your y-axis, your x-axis. Be aware of what data they're showing you and in what way they're showing it to you. Sometimes they're simply trying to make a relationship more clear. Sometimes that person is trying to mislead or lie using that graph. And it's up to you as the consumer or the creator of that graph to know what you're doing or what you're seeing. Another cool thing about bar graphs is that we can actually do multiple independent variables in the same exact graph. So what if we looked at the same data, but now we look to see whether the difference in harassment and non-harassment is different between those who are merely enlisted versus those who are officer rank. And now we see that that difference between the green and the blue bar is slightly greater for enlisted officers, or excuse me, enlisted naval personnel as opposed to officers. Right? And so again, an independent variable of harassment versus not harassment paired alongside the independent variable of officer versus enlisted. So bar graphs are powerful for being able to represent more complicated data than some other types of graphs can easily do. Now, I remember when Microsoft Excel first started to become more powerful and people were using it to create graphs. My parents are both psychology researchers. My dad's recently passed away, but my mother is still around, and they both, for a long time, were stellar psych researchers, right? Publishing a lot of data, going to conferences, and as a kid, I always went to conferences with them. And I remember looking at the graphs that Microsoft Excel could create. And it tended to create what I thought at the time were really neat-looking graphics, but these were also the late 80s, early 90s. And they would have sometimes three-dimensional looking bars, sometimes with crazy little vibrations or patterns on them and colors, and sometimes there'd be pictures in the background superimposed. You've seen graphs like this all the time, right? This is the kind of graph you probably see on Facebook, Twitter, on the news, right? There are always these sort of complicated, colorful, fancy graphs. Now, Edward Tufte, who was a statistician famous for sort of waxing philosophic about graphs, called all of this stuff chart junk. So these are ducks. These are ducks that simply grab your attention and take away from the meaning. In fact, for some reason, somebody created a large duck, I believe in Florida, where else, where you can buy souvenirs, statistics souvenirs. So the idea is that there's a number of these different examples of chart junk. Okay, and I don't care that you remember the difference between Moir vibrations and grids and the actual ducks, these things that take away completely. The idea is that none of these are necessary to represent these data. And so if you stick to the old adage, the KISS adage, keep it simple, stupid, then to create a graph, really all you would need in this case would be your X and your Y axes, properly labeled, and 4 bars. They don't need to be three-dimensional. They don't need patterns. The background doesn't need patterns. There don't need to be pictures. When the point of the graph is to make the data pattern more clear, all the rest of the chart junk merely takes away from it. Another thing you'll frequently see in especially graphs that are presented to you through the media are called pictorial or picture graphs. In this case, you take a bar graph like this, and instead of a bar, you replace it with a picture, like, say, a person. So if I wanted to compare city A to city B, looks like city A has a population of 1 million, city B has a population of 2 million. Now, realistically, in a bar graph, you just make one taller than the other. You don't tend to widen out the bar. But if I just made city B up to 2 million in height, but left him as wide as city A, then he would look like a tall, skinny guy, and it would look like city B was filled with tall, skinny people, and city A was filled with short, fat people. That's not what we're trying to represent. So instead, we have to expand them both ways, and now it looks like city B is dramatically larger than city A, because you didn't just double him in size, you made him larger in both dimensions, which made it much, much larger. Look at this one. This is an actual picture graph that represents annual sales. McDonald's, the largest sort of fast food, fast beverage manufacturer or retailer, takes in $41 billion in sales annually. Starbucks, the far other end of this, is $4.1 billion. So you can see the logo for each place has been drawn up to the height of whatever their annual sales are on that y-axis. So because Starbucks is 4, they're way down there at the bottom, and McDonald's has to be 10 times higher, right? Because it's at 41. But look how many of those Starbucks logos we can fit in that McDonald's. It's way more than 10, indicating, at least suggesting, that McDonald's sales dramatically outpace Starbucks sales, and not merely by this factor of 10, as is indicated by the actual data. So picture graphs are terrible. Bar graphs are much better. Just a simple black bar, color it if you'd like to, for each of these particular retailers with the name underneath. It'd be simple. The point is to display your pattern. Graphs like this are there to entertain, not to make the data clear. Same thing is often the case for pie charts, right? In fact, I love this quote from Edward Tufte. "A table is nearly always better than a dumb pie chart." Right? A pie chart simply takes a circle and tries to represent all 100% of a situation using that circle. Each size of the pie represents how much of that circle or total is dedicated to X or Y. The problem is, it's usually a lot easier to just look at heights of bars that could represent that total proportion than it is to try and compare different slices of pie to see which pie looks slightly larger than the other slice of pie. Right? And so bar graphs tend to be much better alternatives. There is another type of graph that I do like, though, having been somewhat critical here of the pictorial and pie charts, and that's the box plot. So the box plot's really good at representing both the whole range of data, so you can see how far your data really spread from top to bottom, but also shows you where the bulk of the data bunch, where the grouping of the data really are. And so in a box and whisker plot, you have to use that interquartile range information from earlier on. So remember, in interquartile range, you mark the 25th percentile, the 50th percentile, and the 75th percentile. The 25th is quartile 1, the median, or the 50th, is quartile 2, and the 75th percentile is quartile 3. And so for a box and whisker plot, let's say whatever your axis might be. It might be number of sandwiches purchased on National Sandwich Day over the course of many, many years. So you find those various quartiles. Right? And you write that down on that x-axis, or box and whisker plots can be represented vertically if you want. They can go on the y-axis. You write it down along the axis. Then you put a dot above it for quartile 2. Put a dot above the spot on the axis or next to the spot on the axis for quartile 1. Do the same thing for quartile 3. Now draw your box with the line in the middle for the median, lines on either side for quartiles 1 and 3, and then box it in with the lines on the top and the bottom. Then, at the center sides of that box, draw straight lines out all the way to a dot that represents the highest score and the lowest score in your total data, so your overall range. When you're done, you'll end up with a box with these whiskers that go to the minimums and the maximums. Right? So you can see you can actually look at two sets of data that way if you needed to. So airport waiting times, you can see where the bulk of that waiting time is. Most people are waiting between, 4.5 minutes and 3 minutes. I don't know what the hell they're waiting on at the airport that's that fast, but whatever the data represent. The box and whisker plot on the left shows you that that waiting time really isn't substantially different between the busiest airports and the next busiest airports that we see over there on the right. Right? Those two box and whisker plots really sort of overlap. What we do see is a little bit more variability among the middle range of data for the next busiest airports, and a little bit more constriction in the case of the busiest airports, but otherwise very similar. Concerned less about the data, concerned more that you know how a box and whisker plot works, and how in this case you could look at two box and whisker plots sort of simultaneously to be able to compare two sets of data. Just like scatter plots, bar graphs, you can also see outliers easily in a whisker plot. Frequently, if the outlier is far enough away, what we'll do is draw the range to only include all the values without the outlier, and then the outlier will be placed separately as its own dot or asterisk outside of that whiskered range, like this one is here. Lastly, we talked all about figures, but it's worth pointing out tables as well, right? Not always are you going to create a graph. We might create a graph if it helps, but if you only have a small amount of data like this, a table works perfectly fine. A sort of general rule is that if your table starts to have too many numbers, 15, 20 numbers, then your table is going to be hard to read as well, and you may want to think about a visual display. If your visual display is more easier or more clear than your table, then you may want to work with a visual display. Tables are these rows and columns of data. Everything else, a graph or even a picture you decide to include in your paper, is called a figure. All of these sorts of materials go at the end of an APA-style paper in what's called an appendix, and each one gets a label calling it Table 1 with a title, Figure 1 with a title, so on and so forth. Okay? So that's it. That's visual displays of data. Little cheat sheet, right? If you have one interval variable and just frequencies, how often people buy pizza at, different times of the year. Frequency is perfect, right? So you can do a histogram or a frequency polygon here. We talked about those a little while ago. Bars touch, y-axis is frequency, bars, 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 or connected dots. Scatter plots is if you have two variables, especially two interval variables, an interval independent and interval dependent. You place your dots, and you can see patterns. Good for time series as well. If you have a nominal independent variable, or two nominal independent variables, then you're going to want to go with something like the bar graph, right? So that by no means is an exhaustive list of all the charts and graphs you could use. I think more importantly is to think about which one is displaying your data the best. Oh, hi, puppy. Hi, Jakey. Sorry, my dog wanted to come say hi. Make sure that when you label your graph, you're using the same terms on the graph that you used in the paper. So if you're referring to it as, happiness in the paper, don't refer to it as joy on the graph. Keep it the same. Don't use abbreviations, right? Use the whole words whenever possible on your graph so that people don't have to go back to the paper to figure out what the abbreviation is. The graph should also stand on its own. I should be able to look at the graph and understand the story without having to go back and read the paper to understand it. So think about it that way. Your graph should be clear. It should sit by itself, which means it needs a clear title, labels. Use a ruler if you're drawing it by hand, and certainly if you're making a graph for me, you're going to be drawing it by hand or digitally by hand on a drawing app if you need to, but you will not be using Excel or anything else. So make sure it's clear. If you're using colors, God forbid, use them in a clear, simple way, right? Don't use 18 shades of blue to represent your different categories. Big, bold differences. And finally, get rid of all that chart junk. Get rid of all the crap that's in addition that only makes your message less clear. So, sum it up. You got good graphs, you got bad graphs. Sometimes those bad graphs are because people are misleading or lying to you. What types of graphs did we discuss? Scatter plots, limited ones like range frames. Discussed how you can see linearity or the lack thereof using those types of graphs. You can see outliers, line graphs if you connect those dots in the scatter plot, time series plots, bar graphs or Pareto charts. And then finally some advice on avoiding pictorial graphs, pie charts, chart junk. And then lastly, a wrap up with the box and whisker meow plot and some APA style advice. So that's it. That's all visual displays of data. And this is the end. My only friend, the end. All right. Cheers.